Okay, let's get
I
started.
don't even think it required if ever I got one.
Well, maybe they're not requiring it anymore. Then I can check. They used to require 19.
I think it's I'm pretty sure it's a certain grade average.
Okay, then they changed the rule. That might be because so many students were weeded out of being able to take their
I don't think
courses.
I would have been able to.
Okay, then evidently you don't need that anymore.
I didn't do too well. Always.
Okay, so let's get started. So we're going to look at meter sticks now. Now you're going to be doing meter stick labs. So if you balance two masses on a meter stick, right, you're going to have this force times this lever arm must be equal to this force times this lever arm. Now, if we have a perfectly uniform meter stick, the balancing point is 50 centimeters. Now, in the lab, you're going to have to figure out what your center of gravity is. It might not be 50. So my force is the weight. So I have M2G times L2 is equal to M1G times L1. Okay? So we're having the force times the lever arm is equal to the force times the lever arm. Now, you can cancel out the G. So it comes out to M2L2 is equal to M1L1. So here's the problem now. I have 30 kilograms would be massive, but anyway, we're just saying we have 30 kilograms we're going to balance. We have 20 kilograms on the right. It might bend your meter stick, but anyway, we're just going to, just for the sake of simplicity, I did kilograms. And then that's 2.5 meters. Where does that 30 kilogram need to be to balance that meter stick? You have the equation right in front of you. That's 20 kilograms.
Oh.
2.5 is the
Distance for the 20 kilograms, and you're looking at where would you put the 50 kilograms? How far from the fulcrum? Do you have it, Jessa?
1.67 meters.
Okay, so we have 30 kilograms times this lever arm is equal to 20 kilograms times this lever arm. So 20 times 2.5 divided by 30 gives us 1.67, okay? Now, let's say I have um, 3 meters out. I have, it just looks like a mess. We'll say 6.6 kilograms. And then I have, what mass am I going to put at 3.5 meters?
$3.5 for the second one.
Yeah. So we have 6.6 kilograms times 3 meters. Actually, I had 66, so my number's going to be off by 10. But is equal to the mass times 3.5. Connie, what did you get?
I got 5.6.
Yeah, you should have gotten 5.657. This is 56 because that was supposed to be 66. All right, so you should have gotten 5.657. Let's do another one. Everybody got it? So now let's say this meter stick, I've got a 20 centimeters. So now we're talking about places on the meter stick. I'm not giving you the lever arm. You can just figure it out. At 20 meters on this meter stick, 20 centimeters, I have some unknown mass. The meter stick is uniform. It's balanced at 50. At 58 centimeters, I have 50 grams. At 96 centimeters, I have 30 grams. I want to know what's this mass over here.
Wait, is that 200? Oh, no, wait, never mind, 20 centimeters.
That's a 658, you said? 58 centimeters on the first one on the right?
Oh, yes.
Is that say that is that 50?
Yes. So think about what your lever arms are.
Don't have to put the meters and kilograms.
Well,
Or just
in this case, you can just keep them in centimeters and grams. We're going to get out what we put in because we're not getting torque. If we're getting torque, you have to put them into meters and kilograms, you're right. But we're not getting torque, we're just looking for that mass. So whatever units we put in, we're going to get out.
this is right.
Okay, so don't put your lever arms as 20, 58, and 96. Did you do that? Right? You don't put your lever arms as that. What's this lever arm going to be on the left? What's this lever arm? 30, right. The lever arm is the distance from the line of action of the force to the axis of rotation. So this is 30. Did you do that?
Oh, I forgot.
These are just the location on the meter stick, which is not your lever arm. The lever arm is the distance from the line of action of the force to the axis of rotation. The distance from the line of action of the force to the axis of rotation is 30. From here to here. This 20 is the distance from here to here. Just the distance on the meter stick.
I see.
Show me if you have your answer.
I think one of us might be right.
I feel like this is like gearbox and like more ranging shows, so they all do the same dish, but they all do well.
And that's 46, right?
Wait, so 96 centimeters at the end of it, or is that 30 grams?
Well, the midpoint is 50 centimeters, so you do 50 minus.
Wait, hold on, Violet, 'cause I thought Tori got the same thing, and
I get a 50.2.
okay,
I got 54.
59.3. So we have 20, 30 times the mass, and then we have 30 times 46, and then we have 50 times 8
Oh, where did 50 come from?
here.
Oh, that's a 5?
What did I call it?
I thought that was 30.
30 well.
I might have said that. Did I say 30 or 50?
I don't know. I just
I've
looked
been
at the
putting
board
down
and
to
I thought-
30.
Yeah.
Well, maybe I said 30. Then you would have gotten 54. So 54 would be right with a 30.
I was adding the masses and then adding the distances and
Dividing.
Yeah.
multiplying them together. I don't know.
You can't. Each mass has its own lever arm. It has its own triangle.
I got 108.
Do you understand, Lincoln? You can't add these masses. They have different lever arms, right? If you added these, you would get 80, and then add that lever arm. You're off the meter stick. Okay. Now, let's say when I put a meter stick away from the center of gravity, what happens is, and you're going to be doing this in the lab, you model that as if all the mass of the meter stick is at 50. Are there any questions before I go on, Samuel?
Wait, what?
Do you understand this previous one?
Where did you get that 8 from?
Between 58 and 8, this fulcrum was at 50, so this lever arm is 8.
Oh, okay, I see.
50 to 96 was 46.
This the equation.
Okay, did you understand, Samuel?
And so you got between 58 and 96 to get 46.
No, 50 to 96 gave me 46. You subtract, it's the line of action of the force, the axis of rotation, so that's 46. This is 8. This is 30.
Oh, okay.
Okay, what were you saying, Violet?
Is the equation we use for mass times gravity times over r is equal on both sides? Is that only when it's balanced?
Yes, that you have the two sides equal. Okay, now we're still going to be using that equation, but it's just a little bit more complicated. Okay, so let's talk about this. When we have the fulcrum away from the center of gravity, you have to include the weight of the fulcrum in your calculation. Now we're still using the same equation, but this time we're including the weight of the meter stick. Okay, so if you shift this fulcrum here or here, what happens is then the weight of the meter stick acts as a torque. So if we move the fulcrum over here to 75 centimeters, and I have a 200-gram meter stick, which has a center of gravity of 50 centimeters, I want you to tell me what mass do you need to put here to balance it at 93 centimeters? So this is going to be like your lab, so try to pay attention. We move the fulcrum away. You don't get a handout in this lab. You move the fulcrum away. You have to include the mass of the meter stick, which is 200 grams. In this case, you'll have a different mass. It's a uniform meter stick. Your meter stick might not be uniform. It's at 50 centimeters. So now what is this unknown mass here that's going to balance this?
Yeah. So 93 at the end is that?
That's where the unknown mass is going to go at 93 centimeters on the meter stick.
I got 53.
I got 500.
It's going to have to be something substantial to oppose that 200 grams on the other side. So what is the lever arm going to be between the fulcrum and the unknown mass?
Oh, wait,
18.
18. Okay, because your lever arm is from the line of action of the force to the axis of rotation, which is right here at 75. What's the lever arm for the mass of the meter stick?
Oh,
What's that lever arm here going to be for the weight of the meter stick? 25.
$276.78.
Yeah. So we have 200 times 25 is equal to 18 times the unknown mass. This is this lever arm 25. This is this lever arm 18. 25, 18. This is 200 is the weight of the meter stick. This is the unknown mass.
which is this one?
You get 277.8 grams. So now if you're given a lab, and you're told that you have to find some unknown, you have to determine the unknown masses with a meter stick and a fulcrum, you'll know what to do. And then you get your percent error in the end. Okay, you take some unknown mass, you have a fulcrum, you have a meter stick. You cannot weigh that unknown mass. And you predict it, and then you get your percent error. Yes?
Wait, how could you, like, how do you find, like, the weight of the meter stick? Do you just
Well, that
add weights
one
to
you'd
the other
weigh.
side?
Yeah, you just weigh the meter stick. Okay. Let's do one last one. A 200 gram, it's pivoted at 18 centimeters on the meter stick. So you have a 200 gram meter stick. It's balanced at 18 centimeters. What mass goes at 8 centimeters to balance the meter stick?
Wait, would 200 grams be the whole meter
That's the
stick?
mass of the whole meter stick, right?
Oh,
It's on the fulcrum at 18 centimeters. What unknown mass must go at 8 centimeters to balance it? That's where the fulcrum is.
So it's 200 grams.
So just draw it. Draw that meter stick, which is 200 grams, on the fulcrum balanced at 18 centimeters.
And how big is said meter stick?
How big is what?
A meter stick. Or like total length.
100 centimeters on a meter stick.
Oh. My bad. That's-
Show me if you have your answer.
Where's the pivot? Is the pivot like at 18 centimeters?
It's pivoted at 18 centimeters. That's the fulcrum. You should have drawn something like this. It's pivoted at 18. At 50 centimeters, you have your 200 grams of the meter stick. And then you're looking for an unknown mass at 8.
Is that 50?
Yeah, because it's a uniform meter stick.
wait, so is the weight of the meter stick, does it go down at the midpoint?
The weight of the meter stick, we treat it as if it's all concentrated at the center of mass. So the center of mass for a uniform meter stick is 50. Show me if you're done. This is your homework here. You gotta also read that chapter. We've only covered half the material in this chapter. There's a lot of material, and then we have to repeat stuff and all of that. So you should have set it up. Your lever arm here is 10, right? Between 8 and 18. So 10 centimeters times the unknown mass. The other one is 32 centimeters from 18 to 50 times 200. You get a mass of 640 grams. You understand? This lever arm is 10. This lever arm is 32. You have to understand that for the lab.
Oh, wait. I think it's just divided by 8.
Okay, so this is your homework. It's not that much, but we spent the whole class on it, right?
It's a decent bit.
Well, you also need to read the chapter, so I'm not giving you as much. I'm hoping that you read that chapter, because we still have to cover angular momentum.
It's a big chapter.
Well, it covers everything we've done previously in rotation.